Thanks. All right, this presentation is a polymorphic shellcode at a glance by me, Vlad Tsyrklevich. And basically, what we'll be talking about today is, at first, I'm going to basically just do a quick run through about what data basically IDS can detect. And then I'm going to get into polymorphic shellcode encoders and developing fingerprints for them because of weaknesses in their designs. And then I'll talk a bit about what we can do in the future, both for IDS and for hackers. So both detection and evasion on the polymorphic shellcode front. And I'm just Vlad Tsyrklevich. I'm an occasional Metasploit framework contributor and some other stuff. So this is the start of the video, and this is just talking about IDS mainly. And the big question is, I mean, what can we actually fingerprint to, figure out if there's an exploitation attempt? And this is just a small, non-comprehensive list of things, but they're the major ones. And so the first one is protocol anomalies. And that's basically just, it's looking for strange things going on in a protocol that really shouldn't. If you're doing HTTP, you should be doing gigantic binary strings. Say for most plain text protocols. The advantages of protocol anomaly, or fingerprinting protocol anomalies, is that it's very generic, and it can catch a lot of zero-day because a lot of times you just can't avoid having long binary strings. There's just nothing you can do about it. The disadvantages is that it creates a lot of false positives. I mean, not every strange little thing going on is necessarily an exploit. So you might have to do a lot of digging if you have a lot of protocol anomalies going on. It may also be hard or impossible to do for some protocols. If you're doing encrypted links, it's going to be pretty hard to do any sort of a protocol anomaly detection up there. The next one is attack vectors. Basically, it's fingerprinting the basic type of exploit that's going on. For example, if the exploit is something like UFTP siteExec format string bug, you just look for siteExec and then format string commands. The advantages of this is that it always catches the exploit if you can get it to work. The disadvantage is that it can only be written after the fact, and it can only essentially catch old exploits. So it's not really too useful if you're a defender on a network that may be highly critical. If you're a .gov or .mil, protecting against old exploits is nice, but what you really want to do is you want to protect new exploits. And the next one is a specific exploit. If a specific exploit, like one release maybe like DCOM, I believe, by HD Moore for the Metasploit project, had a string like Metasploit or meow in there somewhere, I forget which one. But you can fingerprint characteristics of the actual specific exploit rather than the bug that's being used to exploit whatever is going on. And this is useful when you can basically not attack vector. When this actually occurs, it's not very often. It has lots of disadvantages. It's built after the fact. Different exploits abound. You release it and it's pretty much outdated already because anyone can just modify some ASCII string to change one letter and suddenly, bam, you're past the IDS. The other thing we can fingerprint is no operation instructions, or NOPs. Basically, these are used in a lot of exploits, buffer overflows, stuff like that, stuff where you can modify a pointer somewhere to point to your code. And oftentimes you don't know where exactly your code is, so you had a lot of no operation instructions before your shellcode or whatever your executable code is, so that you're more likely to actually get there because you may not know the exact memory address. The advantages are that it's very hard to evade. If you've got an exploit with a shellcode, it's very likely that you're going to have a big somewhere. You can't just have a anomalous exploit on Linux systems or on a lot of Windows exploits. The disadvantage is that on a lot of Windows exploits, you can have NOP-less exploits, SEH, or SEH overflows rather, or other types of overwrites where you can expect some register to point to a memory address that you control. You can avoid having NOPs by just instead setting your return address to a jump EBX or some other instruction in the DLLs, which are probably going to be static, or rather at static memory address. The disadvantage is also that it can false positive on large binary or ASCII transfers. A list of 50 A's is technically a valid NOP string. It's ECX written 50 times over. So, I mean, this can false positive on quite a lot of data, so it's not always useful to fingerprint NOPs. And the last one is shellcode. Most exploits have shellcode unless you're looking at things like a command execution, or rather made a character injection for command execution, but most exploits generally have shellcode. And so the advantage is that it's almost always necessary. It's almost always going to be there, so you might as well try to look for the most common thing in the exploit world. The disadvantage is that there are many different types of shellcode, different platforms, different types. They do different things, they use different methods. You look at a Linux IE32 shellcode and it does things like syscalls with CD80, and then you look at a Win32 shellcode that actually does symbol resolving in kernel32.dll or other DLLs. They're totally different. They're not alike at all, and they're all written on the same architecture. And as you skip architectures and you skip platforms, things change so drastically that it's very hard to actually fingerprint the shellcode itself. You can also polymorph your shellcode. There are many different possible permutations of a single shellcode. There's many different ways to do things, especially on Intel architecture. Since we've got Intel as a CISC architecture, there's many different possible permutations for every single instruction going on. And the other option is that there's an encoder, which is simply a small stub of assembly before the shellcode that ciphers the shellcode. So what happens is the NOPs run, then the encoders run, and the encoder deciphers the shellcode right in front of it, and then the shellcode runs. And this is useful for a number of reasons, but I'm getting a bit ahead of myself, so I'll get back to this. A lot of IDS systems ignore NOPs and shellcode. If you look at Snort, they have fnord for NOPs, but I believe that's turned off by default. And they have a shellcode.rules, but that's also turned off by default. Both can catch 0 day. I mean, both are in exploits everywhere. So it would be useful to actually be able to use this effectively. It didn't false positive so much or wasn't so hard to implement. NOPs false positive, like I said, a string of 50 A's is a valid NOP sled. Shellcodes can polymorph. Many different permutations are possible. However, the actual shellcode is very rarely polymorphed. What often happens is instead is that it's encoded. So why not try to fingerprint the encoder? Well, here I'm coming back to the shellcode encoders. And the shellcode encoders are essentially small stubs of assembler code that decipher the actual shellcode that's about to run. The usefulness of this is that you can either make your shellcode look like it's not there, because it's actually the encoder and ciphertext. You don't have the decipher text anywhere in the packet. That only occurs at runtime of the encoder. It can also be useful for evading common characters. If you have a hexadecimal 25 or percent sign in your code, it might not be useful for format string exploits. But if an encoder doesn't have that character, you can just encode the shellcode so it doesn't have that character anymore with a specific key. It's the shellcode encoders that are most often polymorphed, because rather than polymorphing the shellcode, which is static, which you have to understand, instead you can just write a shellcode encoder, which is dynamic. And it's easier to write also because it's so small. You don't have to build a whole huge system to understand different types of shellcode like Win32 and Linux. Now you just need a small shellcode encoder which just does memory operations, which just XORs this memory address with this number. And some examples for you of these polymorphic shellcode encoders that you might be familiar with are ADM Mutate, released by K2 and I believe early 2001 or 2002. There's also CLET, which was released in FRAC 61, Article 9, and it was actually more of a research project. made to evade spectrum analysis, and Shikata used in the Metasploit framework. So what is polymorphism? Well, polymorphism is essentially just changing a piece of code so that it looks different every time. But how do you implement this? Well, there are really three main rules of polymorphism. The first, the instructions in the code must be changed to a large number of permutations. So if you're trying to clear a register, you don't just do XOR ECX ECX. You do sub ECX ECX. You do XOR EAX EAX and MOV ECX EAX. Basically, what this is it's just different ways of clearing a specific register. You don't just do it in one way or one or two ways. You have to do it in many, many different possible permutations. And this can be fairly hard because you have to develop a fairly intelligent system to understand how to build these long strings or these long blocks of code that do actually a very simple thing. The second rule is that the instructions in the encoder or whatever the code is that you're polymorphing are rearranged randomly when possible. So if you're using two different registers and they don't depend on each other, you can switch the code around without actually modifying the program. So for example, if you clear ECX and then you clear EAX, you can do that in any order in your code. But if you do something like a clear ECX and then move a value into it, you obviously can't just switch that around. So basically, you just have to rearrange the instructions in your code to as many possible permutations as possible. The third rule is that random no operation instructions are added into your code where it doesn't affect it. So if you have, let's say, a block of code that executes block 1 and then block 2, now instead you can have block 1, tons of instructions that do absolutely nothing, and then block 2. And what this does is it just makes it a lot harder to fingerprint it statically. And I'll be discussing this a bit later on. So those are the three rules of polymorphism, what you have to do to build a good polymorphism engine. These are two assembly dumps of the same encoder. This is an example of ADM mutate. And if you look at these two examples, they're not of the same size. They use totally different instructions, and they don't really look very similar, but they're essentially the same thing. They may use a different key for the encoder, but they do the same function, but they look nothing alike. That is what polymorphism is all about. Some details in the encoders. Shikata is used in Metasploit Framework 2.x and 3.x. The versions vary slightly differently, and I think the 3.x one had some bugs in it which made it slightly weaker. It has approximately 1.3 million permutations, and it uses a 4-byte XOR key. So it ciphers it by XORing a memory address with a 4-byte key, and then a 4-byte key, and then a 4-byte key, and then a 4-byte key. Then there's CLET, which has a built-in support against spectrum analysis. I probably won't be discussing that, but for those of you who know what it is, that's just a little note. It was released in FRACT 61, Article 9, and it has a variable number of reversible instructions. So basically what that means is, unlike Shikata, instead of just doing a 4-byte XOR key, what it can do is it can add a value and then XOR a value and then rotate that entire block of code to the left some number of bytes. So basically you're not doing operation on the memory to decode the ciphertext. Now you're doing a number of variable operations which can change with every encoder, and this makes it considerably harder to fingerprint because you're not just doing the same thing over and over with different instructions. The last one that will be discussed is ADM mutate. It was released as essentially a small toolkit. It had, I believe, encoders for 3 architectures, though only the IA32 one was actually polymorphic. It had lots of NOP codes included, or NOP opcodes included for also 3 architectures, IA32, Spark, and HPPA. And like Shikata, it also uses a 4-byte XOR key. So let's look at the way that Shikata actually works in generating the code. It has programmed in logic, which has a dependency chain. So basically, if you look on this graph, if you look at the top left, there's a box with a fpulns written on it, and that's fpu instruction, and it has a little pointer to a little box saying FNSTN, which is also another FPU instruction on the IA32 architecture. But what this graph essentially means is before FNSTN can run, fpulns has to run. And before popEBX can run, FNSTN must be able to run, or must have run. And for loop block, popEBX, moXorlen, and moXorkey must all have run before you can even get to the loop block. So this is just an idea of how these encoders actually achieve random ordering, because as you can see, nothing depends on clearEcx, fpulns, and moXorkey. So either one of those can be the first instruction. So this basically allows the encoder to randomly put in instructions in random places by putting dependency chains, because this instruction depends on this instruction running beforehand, and this instruction depends on this instruction running beforehand. So there are three possibilities for the first instruction, either fpulns, clearEcx, and moXorkey, and these are dynamically generated so that it changes every time. So for an example of the way the runtime works is a random opcode is chosen that can be run. In this case, it's 3. And in this case, it was a fpulns. So that's the first byte of the shellcode. And then the second instruction is chosen clearEcx. So that's the second instruction. And it just generates this in just random order. And it can create large numbers of permutations because it doesn't have to be in this order. And it also doesn't have to use these same instructions. Going back to the 3 rules of polymorphism, what it's doing here is this dependency chain allows you to reorder it in different ways every time. It also uses different instructions every time, so if you look at the same code generated 2 times, it looks nothing alike. It has different orderings and it uses different instructions. So it's pretty hard to tell that it's actually the same thing. And to an IDS or to some packet filter, it has no idea what's going on. So this is just the code continuing. And this is just a diagram of assembly dumps of 2 Shikata-Ganai encoders. So if you look at them, they're of the same size, but they don't really look that much alike. And so what are the weaknesses in this? If you look at the 3 rules of polymorphism, it has some weaknesses based on its implementation. For rule 1, the many permutations are made for every single instruction. Well, some instructions have few or no permutations. For example, FNSTN, one of the instructions, is always there in every single shellcode. And it's the same 4-byte sequence, so this could be an indicator that the Shikata-Ganai is in that packet stream if an IDS is looking at it. The other thing is it always uses sub or XOR ECX to clear the ECX register, and then always uses the same instruction to move something into that register. That instruction chain also has very few possible permutations on it, which makes it weaker to analysis. The other thing is that ECX is always used as the loop counter during the decoder loop, and the get EIP and looping methods can have more possible permutations. For example, they always use the loop instruction to loop, and they always use the FPU FNSTN instruction to get EIP. There are more possible permutations of this than just that. The weaknesses in rule number 2, random ordering instructions, there are none. It's done where possible and it's done properly. The weaknesses in rule number 3, random NOP padding is added in. Well, random NOP padding is actually not added in anywhere. Rule number 3 is totally ignored by this encoder. So if we wanted to, I mean, there are some static instructions or some instructions that are very few permutations. So we could build a very basic fingerprint, and I'm using snort as the example here. So that first line you see, the content line in the center, is a basic fingerprint for the FNSTN instruction. Like I said, the FNSTN instruction is present in every single encoder of Shikata-Ganai. So this is a very good way to find if Shikata is likely to be in that stream, because if the byte sequence isn't there, then Shikata isn't in that stream. Furthermore, we can look at some other things going on. That second line is a Perl regular expression, and what it finds is the clearEcx code. If you look here, you can see the clearEcx box, and it only has 4 possible permutations. So we use a Perl regular expression to be able to find every single one. The third line is a Perl regular expression that can just catch the ordering of one of the blocks of code. There are very few permutations for the fpulns instruction. Then it fingerprints an fnstn instruction. Then it fingerprints a popebx instruction. And basically what this is doing is essentially the encoder was not built with many permutations in it, so you can build Perl regular expressions to actually find these because there are just so few permutations that a Perl regular is powerful enough to be able to match all instances. However, it's still a fairly weak fingerprint, and many false positives can occur on this because it just doesn't fingerprint on that much data. So is it possible to be more accurate, because this just doesn't really provide us with much? And the answer comes in looking at byte distribution. And basically, few permutations are possible for most instructions, and each byte offset in the encoder has a limited number of possibilities. Well, what does that actually mean? The first instruction in the entire encoder can only be fpulns, moXorlen, or clearEcx. It only has 3 possibilities. And of those 3 possibilities, each one only has a few possible permutations. So we know that the first byte of the encoder is going to be one of the first bytes of those instructions. Basically, in case you're still confused, it just means that certain byte offsets can only have certain instructions because the encoder has very few possible permutations for many of these instructions. And as you can see on the line below, that's a Perl regular expression for the first byte. The first byte can only consist of those characters, 29, 2b, 31, 33, hexadecimal, etc. Those are the only possible permutations for the first byte. And now the question is, can we do this for each byte? I mean, is this really going to give us a lot more capability to fingerprint this? Because if this is the only one that has, let me state this in a more clear fashion. Now the question is, can we do this for each byte offset in the encoder? We know that these byte offsets have only a limited possible amount of permutations to occur in each byte offset. So the question is, can we do this for each one and actually have a small amount of results? Or is each byte offset in the permutation, or is each byte offset in the encoder, I'm sorry, likely to have a bunch of possible instructions, which doesn't really narrow anything down? To look at this, I built a small program which I've encoded in the code.tar.gz file for this presentation. And it's essentially a polymorphic encoder analyzer. It's just a very simple program. To input it, or the input is a large set of polymorphic encoders. So, for example, if I shikaraganai, what you do is you get tens of thousands of possible permutations of this encoder, and you just put them all in a file. And so what you can do with this is you can look at every single byte in every single one of those encoders, and you can say only these bytes actually occurred in all 20,000 or 50,000 encoders. So it's statistically probable that these are the only ones that are going to occur in the entire encoder anytime. To restate that, basically, you look at a large number of these encoders, and if the you look at a large number of encoders, and it's likely that if you have a large enough set, that the first byte of all of those encoders are the only bytes that are going to happen for the first byte, and the second byte of all of those encoders is the only second byte that are going to happen for all those encoders. So what can you output if you have this large set of permutations? Well, you can output the static bytes occurring in every single encoder, because, sorry, there's a train moving through. All right, so what if you have a large set of these polymorphic encoders? What can you really glean from this? Well, you can look at every single one, and you can figure out the static bytes occurring in every single one. You can also build the PCREs, or the Perl regular expressions, as I did here, that one down below, for every single byte offset. You can essentially look at the byte distribution. You can look at the bytes that are going to happen at every single byte offset in the encoder. You can also do spectrum analysis, which is something I'm not going to discuss because it's not really that useful for actually fingerprinting shellcodes and having it be consistent. But if you look down below, I'm sorry if you guys can't see that, but it's just the dot spectrum program being run with the options SBP, which means size, static bytes, and PCRE, or per regular expression, on a file called Shikata MSF2 L1024, which means that it's the Shikata Ganai file or it's a bunch of Shikata Ganai encoders in Metasploit Framework 2 that are less than 1024 bytes. And what it says is basically, I have 20,000 of these encoders, and it says there's a static sequence of D97424F4, which is the FNSTN we fingerprinted here in that content statement. And it outputs a gigantic Perl regular expression. And what this Perl regular expression is it represents every single possible byte that can occur at every single byte offset of that encoder. Now, in some of these, there are many, many possible combinations. For the second byte, it can be any character but 0 and 255. But for some of these, it can only be 2 combinations, like the third line there to the right. It's the only possible combinations are hexadecimal 31 and hexadecimal 83. There are only 2 possible combinations. So this narrows the fingerprint down considerably, because now we can we have something that fingerprints the entire encoder based on the byte distribution of it. And so this is just a large, ugly snort fingerprint, which fingerprints the Metasploit Framework 2 version of Shikata Ganai, which are less than 1024 bytes. And if you can see it, the first 3 bytes are just the static bytes, or the bytes with few possible permutations, and the last line is a Perl regular expression for the byte distribution, which should narrow it down so considerably that there are few to no false positives anymore on this fingerprint. Because without that byte distribution information, there's going to be false positives all over the place, because that's just not a very good signature just by itself. And so just a little on this fingerprint in case you guys are planning to drop it in. The Shikata Ganai signatures change between Metasploit 2 and 3. It also changes if the payload, or if the actual shellcode the encoder is encoding, is less than or greater than 1024 bytes. So if you guys plan to drop it in, realize that the code.tgz file should have the full signature, but the signature here is only for Metasploit Framework 2. And so that concludes the Shikata Ganai section, because we essentially built a fingerprint for what is supposedly a polymorphic shellcode encoder. Okay, now we move on to CLET. CLET, like I said, uses a number of a variable amount of reversible instructions, which, like I said, means instead of just using XOR, they can use multiple instructions. They can use, in this case, they use roar, or roll, XOR, roar, add, roar, which, if you don't know, I-32 assembly means absolutely nothing to you. But basically, they use around 8 different instructions to encode this, so that it's a bit more difficult to look at. And the CLET encoder throughout all of the generated CLET encoders is pretty much split into 3 parts. The first part is in that little red box, and it's just the initialization. It sets up all the pointers, and it sets up all the values. The middle part actually does the ciphering. It moves the byte values around. And the last part does the looping, so it loops and it moves the loop counters and everything. So it's essentially split into 3 parts, which can essentially be thought of as totally, which can essentially be thought of as totally separate. And so what are the weaknesses in this encoder? Well, if we look at rule 1, which is the random instructions rule, some instructions have few or no permutations. In fact, if you look at it, the starting and ending sections have almost no permutations whatsoever. It's only the middle section that has a large amount of variable permutations, because they use different instructions. They don't just use XOR, they use add and rotate and things like that. Rule number 2, random ordering. Again, they only do it in the middle section. The start and ending sections are totally vulnerable. And rule number 3, random not padding. It's not done at all anywhere. And so what this tells us is that basically the starting and ending sections are totally vulnerable to analysis since they're basically not polymorphic at all. And I'm running a bit short on time, so I'm going to speed this up a little. And basically, only the middle section varies in length, so different clet encoders differ in size. And this means it's impossible to do effective byte distribution analysis like we did last time, unless we want to fingerprint just the start and the end, which is what we want to do. The middle section is almost impossible to fingerprint just because it changes so much. It's truly polymorphic. But the starting and ending sections change much, so we want to fingerprint those. So what we do is we get a large amount of clet encoders of the same size. Like for example, 42 bytes is what I used. And that means that since the middle section is the only one that changes and that changes in size, and the starting and ending sections are always the same size, that means that all 3 sections are the same size here. In case you didn't understand that, basically, if the middle instruction is the only one that changes, and all of these encoders are all 42 bytes, that means the middle section is the same in all of these sections in terms of length. So basically, I got a bunch of 42-byte clet encoders, and I used that as input to Spectrum, and I got that last line right there, the Perl regular expression. And the top 4 lines are basically just fingerprints against static bytes, and just problems with the first rule of polymorphism, because a number of bytes in this, the top 3 lines are for static bytes. As you can see, they're just content, they're just looking at plain bytes, they're not even Perl regular expressions. The last 2 lines are Perl regular expressions. The first Perl regular expression is a fingerprint for the starting section, and the last Perl regular expression is a fingerprint for the ending section. And all I did was I just took a bunch of these encoders of the same size, and I just fed them into my Spectrum polymorphic shellcode analyzer. And so this is essentially another fingerprint for what was a polymorphic shellcode encoder. My favorite. These are the 2 assembly dumps that I had showed you earlier. They are 2 versions of ADM mutate. For the random instructions, all instructions have very few permutations, but they have some permutations, unlike clet or Shikata-Ganai in some instances where they had none for some instructions. For rule number 2, random ordering, however, they only switch around the sequence of 2 instructions, so they really don't do rule number 2 at all. And for rule number 3, random not padding, it's done everywhere. So this makes it considerably harder, because now we have NOPs everywhere, and it's much harder to analyze. Byte distribution is possible. Random not padding means that every single ADM mutate encoder is going to be of a different size. And because it's of a different size, for example, it's 81 bytes, or 82 bytes, or 83 bytes, that means that our Perl regular expression has to be fitted to each single size. So we have to have an 81-byte ADM mutate fingerprint, and an 82-byte ADM mutate fingerprint, and an 83-byte ADM mutate fingerprint. So this really isn't that useful. So what we're going to do here is we're actually build a fingerprint. And if you look at ADM mute engine definition file, or ADM mute-enc.h in the ADM mutate source code, it has all the possible permutations for the instructions. And I think the maximum permutations for any instruction was like 4. It's very low, but all of them are polymorphed to some degree. Like I said, there are a very small amount of variable instructions. I mean, they all change, but there's really not that many possible ones. And jump offsets is something I'm not going to talk about since I'm running a bit low on time. If I have time at the end, I'll get back to it. It's nothing too crazy. The example on the right is an assembly dump of some ADM mutate code, except what I did is I put red dashes across all the NOPs so that the NOPs just didn't bother us when we were analyzing it. And then I wrote simplified pseudocode for every single instruction that goes on. So if you look at the pseudocode on the left, that will describe every single possible ADM mutate encoder that ever happens. The only thing is those instructions on the left can be polymorphed in about 2 or 3 ways. But since we know the ordering of each instruction, except the 2 interchangeable ones, which can change every time, we can essentially just hand build a fingerprint or hand build a Perl regular expression to fingerprint these instructions. And the way we're going to do this is, since there's a bunch of NOPs or occurring between every single instruction, what we can do is we can just place a fingerprint for one instruction and just say there may be a variable number of bytes that, maybe 0, maybe 20, and then we'll say another instruction. Basically, let me repeat that because I was sort of unclear. What we're doing is we have the fingerprint for one instruction, then we just say there may be a bunch of bytes in here, but this is the next instruction, and then a bunch of bytes in here, but this is the next instruction.
So you're basically just fingerprinting the control flow instead of the individual instructions?
No, I mean, we have to analyze the control flow, but we're still fingerprinting the individual instructions. We just have to take into account the fact that they're random NOPs. We just say there may be random stuff here because there's random NOPs, but these 2 instructions have to occur. It's just that there may be random stuff in the middle. And so if you just look at the adm muteng.h file, it's very simple. And, well, very simple. Never mind. This is the snort fingerprint that I developed for ADM mutate. And again, the top 2 content lines are simply static bytes. The lower line is a Perl regular expression for the actual fingerprint, and it's just handwritten. And as you can see, it has the first instruction, EB26 to 7A, and then .0 to 20 means there can be either 0 or 20 random bytes in between the first instruction and the second instruction. So that takes into account the fact that random NOPs may be in there. So again, the last fingerprint for another supposedly polymorphic shellcode encoder. And these are the 3 biggest ones, and actually only the only 3 that I was able to find. So now we've just developed snort fingerprints for every single polymorphic shellcode encoder that Google showed on the first 2 pages. So now that we've defeated all these polymorphic shellcode encoders, what's the future of detection? I'm going to skip over X-rays because I'm sort of running low on time, and emulation. Well, I may get back to that, but dynamic translation. Dynamic translation is essentially where a single program can understand assembly code, and what it does is it just follows the assembly code in a packet. And if it finds that that assembly code looks like an encoder, for example, it goes down and it loops back up and changes some memory, and goes down and loops back up and changes some memory right ahead of that, and it just keeps doing it. What it'll do is it'll wait until it deciphers the whole shellcode, and it'll try to fingerprint that shellcode. So dynamic translation is essentially just an intelligent assembly parsing. It's just an intelligent assembly parsing program that can just look at packets and see if there's a polymorphic shellcode encoder in there. The problem, this is a pretty heavy operation. If you're trying to run this on all packets on a high throughput, on a high network, you're going to get screwed. It takes too much time. So the other option is that we do scoring systems. The fingerprints that I showed you today are pretty heavy. I mean, they have gigantic Perl regular expressions, and while they may have few false positives, the downside is that they may be pretty slow. So what we can do is we can just have scoring systems. We may not be able to say that every packet has a shellcode in it, or we can infer that if a packet has NOPs in it, it may have shellcode. And if a packet has protocol anomalies in it, it may have NOPs. Basically what this means is that we look for the lowest common denominator first. It's likely that if there's an exploitation attempt, there's going to be a protocol anomaly in there somewhere. And it's likely if there's a protocol anomaly in there, there may be NOPs. So basically we do the most simple processing first, and if that goes through and says there's something suspicious, we do more and more processing. So first we look at protocol anomalies, then we look at NOPs, and then we can use these fingerprints, and they may be very heavyweight, but if they're only run on 0.0001% of the packets, it's almost no speed hit at all. You just have to be intelligent in your scoring system. The benefit of the scoring system is also that you can do scores. I mean, if you're a .org no one, maybe a score of 1 is reasonable for you. If you're a .edu, maybe 0.5. If you're a .gov or .mil, maybe you just want 0. so it also allows for variable amounts of protection. The future of evasion. Well, the real future is just implementing all three rules properly. I mean, none of the encoders we looked at actually did that. All of them were missing some key feature or just really skimped on some things. So just do it more in depth and do it properly. I mean, polymorphism can be done on shellcode or it can be done on encoders. I would actually say that focusing on polymorphic encoders would be better for now, because polymorphic shellcode is simply so complex that it would take a long amount of time to write a polymorphic shellcode or a polymorphic shellcode engine, and it may not just be worth the effort, and it may just confuse you and make your program worthless because you just made slight errors and it wasn't really useful. While a polymorphic shellcode encoder is fairly simple, right? And as long as you just don't screw up some simple things in the implementation and know what you're doing, it's not going to be too hard to build an effective one. Typo. So what can you do other than actually do polymorphism correctly to evade IDS? You can use low-level OS details to break dynamic translation. Like I said earlier, dynamic translation just understands basic assembler. So if you're running an IDS and like a scoring system, let's say dynamic translation, that dynamic translator will understand. Oh, okay, it just moved a key into some register and it's XORing with that key. So what you can do is you can use OS-specific details to bypass dynamic translators. Dynamic translators don't know anything about the memory space layout of Windows or Linux. So if you know something static, for example, the ELF fingerprint at the start of pretty much every single ELF file, which is OX7F ELF, that it's always going to be at one address. What you can do is you can just move a static memory address into a register and copy the data at that memory address. Now you know what it's going to be every single time, but the dynamic translator is dumb. It doesn't understand anything about operating systems. It doesn't know anything about common memory space layouts. So what this can be done, or what this can do, is it can essentially just bypass dynamic translators because they're too dumb to know anything about the memory space layout. Let's skip better exploit side technique for now. Using instructor-specific or obscure instructions may be useful for breaking dynamic translators temporarily. Dynamic translators are going to understand the basic instructions. They're going to understand XOR. They're going to understand move. They're not going to understand, instructor-specific instructions or instructor-specific instruction sets like 3D Now, which is on AMDs but not Pentiums, or SSE2 or MMX or other, uncommon instructor-specific instruction sets. So this is a fairly weak approach. It can be pretty easily bypassed by just adding some new instructions. But if you're in a bind, this may be something to look at by, writing MMX polymorphic shellcode encoders. How much time do I have? I'm fine. All right. All right. Well, does anyone have any questions? I mean, I can cover some other things here. I'll take some questions. I'd rather take questions.
Quick question about the smart sticks. Have you actually flown those in a production environment with a lot of traffic? And if so, what was the false positive rate?
No, I haven't. I don't own one of those types of networks. The only thing, supposedly, no. No, I haven't. I'm not the type of person who is at that level. And in fact, I will tell you that the speed hit will be significant. I can tell you that the false positive rate will be pretty low, but the speed hit may be significant. I mean, the thing about shellcode is that you need to run it on all ports, or at least that's the default setting. But I mean, if you're like running a server and inbound port 80 is like a Apache and inbound port 25 is like a SendMail, you'd be better off just running the shellcode just on SendMail, because that gets owned every 2 months, while it's pretty stable. So you can be sort of smart in your filtering, and that can also just help reduce the speed hit of using these signatures. But I mean, I think the real key here would be to actually build a scoring system or build some sort of I forget what the name is exactly, but there is some sort of snort feature where if one signature says, yes, this signature just happened in some packet, then another signature activates for that stream. So it's just if this, some NOPs happen, like the shellcode or something like that. But if you want to get into it, you can make this considerably faster.
The Chicago 9 for version 3 is slightly weaker than version 2. Can you elaborate on that a little bit?
You know, I did all this research about half a year ago. God. Basically, a couple of the dependencies are sort of screwed up. For example, if you look here, it says clearEcx and then moXorlen. So it should be able to occur in any random order. You know, you can have clearEcx and then fpulns and a bunch of stuff and then moXorlen. Well, one thing is that clearEcx occurs and then moXorlen occurs every single time. It always occurs in that same order. So I guess one of the dependency structures was just screwed up in the version 3. And if you look at the PCREs, they're also slightly different. The shellcode.rules files included the code.tgz file. So you can check that out for yourself. But I forget the exact differences.
Are you doing testing like host side, or like doing for you that are doing your spectrum? Are you doing like this host side, or are you actually doing this wire?
I'm just doing it host side. I basically just generate a bunch of encoders on the host using the MSF encode utility, which is included in the Metasploit framework. I just create a bunch of different ones, and I just dump it into a file with a specific file format, and then Spectrum or Spectrum.c can understand that and look at it and tell.
What level of success are you having right now as far as, you know, for the stuff that you're generating? What could be like percentage-wise as far as
What percent of Chicago 9 encoders is caught by this? 100%. Yes. Spectrum analysis itself could be used for getting slightly fuzzier fingerprints, but slightly faster, if you're familiar with that. But I wasn't into the whole fuzzy thing. I always wanted 100% or nothing, so I built it like that.
So for all intents and purposes, version 2 is actually
Yeah. It's just, yeah. Should I get off or? All right. That's it, folks. Thanks for coming by. If anyone wants to complain at me for talking too fast or look at some of the slides I didn't cover, I'll probably be outside for around half an hour or, well, probably for like 10 minutes if you want to bug me for a while.
Listen, if you do want to build a high traffic network,
Joe, on your call for paper.
On my what?
Your call for paper?
Oh, thanks, dude.
That was a fun little reversing thing, you know.
Yeah. If you look at it, it's actually a lot simpler than
Yeah, I know.
Yeah,
I
it's
actually after I looked at all the code and I was like,
yeah. That's just the common, and it's a bunch of go-tos, and it basically
right.
does nothing, but
what
it
was
looks
funny
nice.
Is that I wish I would have done just like a basic statistical analysis, like on because you had so many of the same things. Like, oh, I can
Yeah.
figure that's a space.
Yeah.
That's a this.
Yeah, it was not meant for
Right. I mean,
cryptographic,
think outside the box. Yeah.
Yeah.
Good talk though.
Are you gonna post Spectrum for like your Spectrum?
It's on here if you want it.
I didn't bring anything on.
If you want, you can email me at my address. It should be
Does Vinny have a copy? Or
Vinny who?
Luke?
You know, you can just, do I know you by chance?
Maybe.
I know Vinny.
Yeah.
Yeah. I mean, if you want, just tell Vinny and I'll drop you a line or something. But
I was supposed to roll down here with Vinny and Patrick, but they because of work things.
yeah, yeah. But I mean, if you want, just email me or tell Vinny, and he knows where to find me. Cool.
All right, that'll work. Thanks, man.
later on, after the convo, when we're back in control room, settle down, if you really want to do some performance testing,
Yeah. Too much work. I'm sorry.
no, I'll take it over. I'll do it.
Hey, if you want to do it, man, the code's out there. Sorry about that. Oh, no problem. You know, stuff happens. Yeah, it's fine.
It's Vlad 902.
Yeah, Vlad 902. Yeah.
Cool, thanks.
Sorry about
What is your topic? We can look at this thing. generally he was introducing this room, so I don't know if there's anything, if he's back yet or not. There's anything introduce you.
No, there wasn't. I just said my little spiel.
Okay.
Oh, I think he went out to Sips, and right, he came back, but the rest stayed back to get some takeout for the rest. Cool. Yeah, I was a bit. I started out a bit late, so I got that. It was alright. I skipped one thing, which I basically said in my slides. You can do this, but I didn't because byte jump sucks. And the other thing was, you can do this, but it's too slow. So I just skipped the sort of things that are theoretical, but